Title of our presentation is Multitask Evaluation Models Positively Impacting the Application of Ergonomics. I'm Murray Gibson, founder of Saturn Ergonomics, and also a PhD student at Auburn University and a licensed professional engineer and certified professional ergonomist. My co-author is Bob Sesic. He's a fellow PhD student at Auburn University. And Bob and I collaborate on innovations and ideas in ergonomics and developing new technologies. And Bob has extensive experience with patent development and innovation processes. Okay, what do we think of when we think of a single task job? Typically, you think of something where someone does the same thing over and over. So that's what basically the definition of a single or monotask job, such as the one in the video here. Okay, most of the risk assessment tools that are currently used by the ergo community are single task models. They were really designed for a single task profile with the level of the different risk factors for force and posture, duration. They typically accept one level input of an input to the model, so it expects to see the same thing every time, something similar to this. Okay, but in reality, when we look at jobs to evaluate jobs, we typically see something more like this. We see variation in the magnitude, the duration, the frequency, and so things are variable, but we're forced to put it to, and typically we do that by using an average, say for force, or we're sometimes you're cautioned in the paper that if you don't use the average, to be more conservative and use the worst case. Well, we're going to show subsequently in the presentation some of the problems with doing so. This is a kind of a timeline of the more well-known ergonomic evaluation and risk assessment tools. And notice that most of the models are single task, the ones with the black dots. But notice some of the more current tools, the last 6 or 7 years, the tools have color dots. The red are multitask, what I would call naturally multitask, and the blue are what I would call statistically multitask, where you use some type of statistical weighting to be able to evaluate different tasks independently and then cumulatively look at the resultant metric. But the naturally multitask ones, the RCRA, and then the various fatigue failure type tools out of Auburn University, lift, duet, and the shoulder tool. Okay, naturally multitask, I want to define that is models having a metric output that naturally accumulates or depletes as work tasks are completed. So you can have an accumulating or depleting metric output, and so over time the accumulating bucket is going to fill up, and the depleting bucket is going to empty. And you can see as tasks are performed, one bucket accumulates and the other depleted. Well, the current multitask models that sort of fit one of these definitions is fatigue failure is accumulating. Tissue damage accumulates as work is performed over time. And then an example of the model using depleting metrics would be the recommended cumulative recovery allowance, because your in-cycle recovery is depleted as you apply forces. That opportunity for the muscle to recover, the time available within the cycle is depleted, and that's something that can be quantified. Advantages of multitask models: improved analysis accuracy and consistency. They accurately reflect the impact of small incremental changes. You can model job rotation path exposure, calculate a cumulative exposure dose. They have high application utility and enable targeted solutions. Okay, let's look at improved accuracy and consistency. This is a hypothetical linear relationship. So the x-axis, think of that as your input to the model, and then the y-axis would be the output. So this is a linear relationship. The rise over run or slope of the curve is constant. So if we make a 20-point move on the x-axis, on our y-axis on this particular line, we make a 6-point jump. And if we look at a further along the x-axis, a higher value, if say if we go from 70 to 90, we also make a 6-point jump. So it doesn't matter if you move the same amount on the x-axis, wherever it is on the you're going to have the same output or rate of change on the y-axis. Okay, so something like this. You can see it's the same for both the lower levels and the higher levels of x, the y output. Okay, now let's look at a nonlinear relationship. Now, one thing interesting, most of the multitask models have nonlinear relationships, so that line's not straight. It gets very steep. Typically, it gets steeper, particularly for higher force exertions. I know for the RCRA and fatigue failure models, and with this revised strain index, is the higher the percent MVC or the percent of maximum effort. At the higher levels, the curve is much steeper, and so the multiplier increases accordingly. Increases faster. So let's look at this nonlinear relationship. Say we move 20 points lower part of the curve, we have a 2.5 jump on the y-axis. Now, if we take that from 70 to 90% MVC, we have an 8-point jump. And you can see, so we move the same distance on the x-axis, but it's due to that steepness, you tend to climb that curve. And kind of the takeaway there is that higher forces are typically more severe, with the result is there as far as their impact to the metric, the output metric with these newer multitask models. So you can see the summary there. Due to the steepness of the curve, the higher percent MVC values result in a larger jump up the y-axis, and your multiplier is higher. Okay, models with nonlinear relationships, say the Romer endurance curves, the fatigue failure theory, the Potvin MAE equation, ACGH, TLV. Currently doing a lit review of looking at 40-something tools, but these to see which ones have a nonlinear relationship. But these are tools we definitely know. You can see it's not a straight line, and typically it's for example with the MAE equation is duty cycle, and a lower duty cycle or percentage of the time force is applied, it's acceptable to have a higher MAE, or the maximum acceptable effort. So if you're not doing as much as something, you can apply a higher force. Okay. Now let's look at the MAE can be transformed into the RCRA, or recommended cumulative recovery allowance, using algebra and substitution. We get a new equation. In this equation, we can take the duration of the effort, the frequency or number of times we do it, and then the magnitude of the effort as a percentage of maximum strength, and calculate the recovery time needed for the muscles involved to recover, so we can prevent undue level of fatigue. Okay, this is a force time profile. We're going to use this. I'm going to get us introduced to this one so we're familiar with it, but I'll demonstrate how we use the RCRA model with this one. Notice we have a 60-second cycle from start to finish, so this is repeated over and over. You have 4 big forces that are 66% or 2/3 of the 25th percentile female maximum strength, and then we have 4 little forces, 10% MVC, and all of these forces are 0.75% seconds in duration. So out of that 60 seconds, we're applying force for 6 seconds, and the rest of the time, the white space is in cycle recovery time. Okay, well, how do we calculate that? Sort of just told you, but we have it. Say you take the cycle duration, and then you can see in the calculations at the bottom of the slide, you just subtract the force application time. So 4 times the 3/4 seconds in duration for the big forces, and then 4 times the 3/4 seconds for the little forces, and we come up with 60 minus 6 seconds, or 54 seconds of in-cycle recovery. Okay, this is a RCRA visual model to help us understand how the model works. And notice we have a 60-second cycle. We have force applied for 6 seconds. In the remaining time, sort of that white space in between the forces, is the in-cycle recovery time. And how do we know if that's sufficient recovery time for those forces that we applied? Well, we do that with the RCRA. It calculates model recovery time. So we have the inputs of the magnitude, frequency, and duration, and we can adjust for posture. So we know the characteristics of what we did. We can, when we apply force, we can calculate how much recovery time is needed for the muscle to recover from that to prevent the onset of undue fatigue. So this shows calculating the recovery time for the big forces and for the little forces. We plug those values, the duration, the count, the percentage of maximum strength into the equation, and we get a model recovery time for the 4 big forces, about 270 seconds, and model recovery time for the 4 little forces, or about 2 seconds. So roughly about 271 or 2 seconds in total are needed to recover from those force exertions. So let's start it where we were. We had our 60-second cycle, and we see we're applying force 6 seconds. So what we're left with is 54 seconds of in-cycle recovery. So the muscle's active for 6 seconds, and we have 54 seconds within the cycle for the muscle to recover. Well, let's look at, if we throw those little force recovery times in there, you can see that only 1.7 seconds was needed. We'll still have about what we had to begin with. We'll have 52.3 seconds of recovery time left. But now let's look at the impact of the 4 big forces. It was about 270 seconds. Notice we really just blew out we didn't have nearly enough recovery time, that 54 seconds, to account for that. That's the little area in the dotted or dashed line. So we calculate when we don't have sufficient recovery time. Well, the main metric for the RCRA is a ratio of the model recovery time divided by the in-cycle. So in this case, we had 54 seconds of in-cycle recovery, and our model recovery time we calculated for those 4 little forces and 4 big forces was 271 seconds in total. So we needed the ratio is 5.0. So we needed, if it had been less than 54 seconds required to recover, our ratio would have been less than 1, but we just blew that out with this example. It was 5 times what it should be, or what it needs to be, so you don't have the onset of undue fatigue. Well, how do we interpret that 5.0? Well, the ratio of model recovery time to in-cycle recovery time, we have a suggested color coding. If it's less than 1, that means that what we calculated, the model recovery is less than what we have, so we're in good shape. But if we don't have sufficient recovery in cycle, then you can use a color coding to sort of sort out the kind of the worst offenders, or the ones with the higher ratios would be the higher priority. Okay, this is a example force time profile. Again, our 4 big forces and 4 little forces. Here we're going to look at the impact of using the average and worst case model inputs. And one thing I'm going to say is you can't run a single task model multitask, but you can run a multitask model single task, and you can do so by, instead of evaluating each task or force independently and then totaling it up at the end, we just have a single input of an average or the worst case. And so what happens is our actual force profile that we had here, the big forces, 4 of them, and then 4 little forces, we either compute an average, which you wind up with about 38% MVC, 21.2 pounds. There's still 3/4 of a second in duration. And if we use the worst case, notice we look there. We count them all like the highest one, 66% MCV, and we plug that into the model. So that's typically when you use a lot of the traditional models. This is exactly what we're forced to do. You can use the average, or you can be more conservative if you use the worst case. But you might say, well, I don't do either one of those. Well, if you don't, what do? You know what? You have to do something. Otherwise, you're just sort of winging it and adjusting things. But to have some consistent basis, so people can be consistent applying the models, you have to have some rhyme or reason behind your inputs. And usually it's using the average of the worst case. But this shows the recovery time calculated for that force time profile. And notice the multitask, we calculated 271 seconds. That counts the magnitude of the forces for what they actually were. But when we use the average, notice our recovery time calculated was only 38 seconds. So it was significantly lower than when we ran the model multitask. And notice when you use the worst case, we way overstated it. And much of this presentation came from a slide I saw Dr. Richard Sessick. This was back in 2015. It said that the average usually understates the risk, and the worst case usually overstates it. And that was sort of our intuition. And later, as I became a PhD student at Auburn University, I decided, hey, I'm going to see if I can, that makes sense. Let's see if we can run some numbers with it or actually calculate it. So this is the kind of the fruits of doing that. But this shows how, again, the average understated it, the worst case overstated it. Now this is looking at the summary. If we look at the ratios, the RCRA recovery time, and then the difference in running the model multitask versus running it single task and worst case, which is also another version of running it single task. But notice that running it single task, the actual RCRA ratio is 5.0, which is it's way too high. It's 5 times what the recovery time is needed. Is 5 times what it should be, or what we have available, I should say. And notice that when we ran the model with the average force inputs, it said it was okay. It said we had sufficient recovery time, 38 seconds. Remember, we had 54 seconds of in-cycle recovery. And notice when we ran it worst case, it said it was really bad. It was 10.0. So the kind of the takeaways there is when you use the average, you're typically going to understate the risk. And this is an example here, though, where we might have said, hey, this job is okay, when it's not okay. It's not even close to being okay. Or we said it was a 10.0, twice, double what it should be, 100% difference in the wrong, too high. So we're going to have lots of situations where we kind of condemn a job and say, hey, this job is problematic or at risk, when it may not be. It could just be because we used the worst case and we overstated it. Okay, I'm going to show how to accurately reflect the impact of small incremental changes, and that's one thing multitask analysis helps us do. And this is a common scenario. We either add a force, say you make a change, lean team makes a change to a job. Maybe you add a step, or you add a force exertion, or maybe we remove 2 fasteners, maybe do line balancing and you get rid of 2 things, or you add things to it. And you get nonsensical results. And in the past, I'm working with teams, ran into all kinds of situations to where things would happen using single task models, and you're like, this just doesn't make sense. And now I kind of better understand what probably happened. And a lot of it is attributed to using the average or the worst case, and the inherent error in doing so. But in this example, we're gonna remove two of those little forces. We're gonna say, okay, we made the job a little bit easier. We eliminated the need to apply those 2 forces. So poof, they're gone. So and now we only have 4 big forces and 2 little forces remaining. Okay, so this shows that if we use the average, our average before we remove the forces was 21.2 pounds. After we remove those 2 little forces, our average, look what happened to the average. It jumped up. So despite we get that about 1.5 seconds of recovery time back because we don't have to apply those forces, but by increasing the average, that's going to be probably more detrimental than the time saved. So let's look and see how. So we look at before or after of the actual recovery time calculated, and we would expect. What would you expect if you remove 2 little forces? You'd expect your resultant metric to get a little bit better. Probably nothing to get excited about, but you should see it move in the right direction. And it actually does. The recovery time goes from 271 seconds to 270. That's not much, but we made the job a little bit easier, so the recovery time needed for the muscle to recover was a little bit less. Now, but notice for single tasks, we made the job easier, but we jumped up from 38 seconds. And it was too low, our rating was too low to begin with. Remember, it was green, said it was okay, but we jumped up from 38 seconds to 61 seconds of recovery time needed after we removed those forces. So we made the job easier, but the score got worse. Now, notice when we used the worst case, that's where we assumed they were all like those 4 big forces. Even those 2 little ones left were going to be the 2/3 of your maximum strength. But we just see here that we moved in the right direction. We made the job easier, and the score came down. But still, it's way too high overall. Okay, and we see this kind of the output summary here when we remove those 2 little forces and kind of the nonsensical results that we get. But if we look at the RCRA ratio, we improved a little bit. We went from 5.0 to 4.9. I tell you, that was right on the edge of to even drop well, because it only dropped 1 second there. Now we look at the single tasks, running at single tasks using the average. Notice that we said it was okay. Now we said it's a problem. So we made the job easier, but now it turned from green to yellow. And look at the worst case. Again, it moved in the right direction, but it still it's too high overall. But it's not as bad. And it's interesting to me that a lot of times it depends on the example that you choose, the job that you've evaluated, or if you're coming up with a hypothetical example. It depends on the levels you choose. But I found that a lot of times the worst case has less absolute error than the average. But anyway, this is everyone, examples you choose are kind of different, but this is kind of interesting here. Okay, well, you can also model job rotation path exposure and cumulative exposure dose. A little basics on fatigue failure theory. Ultimate stress is how much force does it take to break something. We're looking at a tendon. How much force is necessary to break it with 1 repetition, so 1 pull. Lumbar disc, it would be what's the compressive force required to break it. N is cycles to failure. So at 100% of ultimate stress is where it breaks. And for example, with a tendon, that's about 1.4 times your maximum strength. But now, if we're looking at what our cycles to failure are, whatever our ultimate strength is, the force that broke the tissue, at a lesser percentage than 100%, it's going to take more cycles to break it. It's not going to break just with 1 pull. So if we say we go to 90% of the ultimate strength, it may take 5 to 10 forces, and if we go to 50%, it may take 1,000. And then you go down to say 20 and 10% of ultimate strength, it could take several thousand forces to break the material. And this is taking the sort of the material science techniques and applying it to human tissue, which is a kind of organic application of that, I guess. So we have cycles to failure. So at different percentages of maximum or at the ultimate strength, you have N cycles to failure, and then N is the exposure count. If we're observing a job, say we're looking at 10% of the maximum, 20, 50%, whatever, at whatever percent of the ultimate strength level, N is the number of times they do that. So you apply forces at maybe a certain magnitude. Okay, we had so many forces at that level, but notice the cumulative damage is N divided by the cycles to failure, and so that's additive. So the higher forces that are applied, you're going to have much lower number of cycles to failure than than the lower forces applied. So say if it was 10,000 cycles to failure in, and I had did that 10 times, that's 10 divided by 1,000. And say if it was 100 cycles to failure and I did 10, it's going to be 10%. It's going to be much higher. 10 divided by 100. But that shows you the basis of how that's the basis of how the fatigue failure theory is additive in nature, and it also looks at different force levels independently, and so you can look at the cumulative impact. This shows the ultimate stress versus cycles to failure. Notice the x-axis is logarithmic, so it increases by orders of magnitude of 10. So, it goes from 1 to 10 to 100 to 1,000. So that's what enables us to do a straight line. Otherwise, it's a very steep curve right there. But it shows for tendons, ligaments, and lumbar disc. Okay. This shows sort of that I was telling you about, how we could calculate cumulative damage. Say we had 500 cycles at 40% of ultimate strength in the table, and so cycles to failure is 100,000. So we take 500 divided by 100,000, and then we had 75 at 50% with 10,000 cycles to failure. So 75 divided by 10,000, and you add that up, and then you get a cumulative damage. And the way the models work is for different cumulative damage levels, it calculates injury risk probability that's developed using epidemiological database for different levels of cumulative damage. Okay, this is Auburn University has a web page where there are versions of the fatigue failure tools, lift, duet, and the shoulder tool. So one's for the lifting, the other's for distal upper extremity MSD risk, and the other one's for the shoulder. Okay. Now, also we can look at these. Now, the RCRA is good to look at the work content within a cycle to make sure we don't get overloaded and have more physical work content than we can recover from in the cycle. One of the strengths, but it's not necessarily that good at looking at cumulative exposures. There's ways we can do that, but really the fatigue failure theory is more suited to looking at cumulative exposures. And for example, a job rotation path exposure. We look at, say, we're in a plant and we see there's a work area layout. We have these different stations, and then we see, there's a job rotation schedule. Every 2 hours, people rotate into a different station. Where their cumulative exposure, say of employee 3, is the 2 hours they spend at station 3, 2 hours at station 4, 2 hours at station 5, 2 hours at station 1. That's the actual job rotation path, and the individual's exposure is dependent upon where they've been. You can have risk ratings and all by station, but really it matters what the path was. What did they do? There might be one of these jobs that's really difficult. Maybe today that wasn't on their schedule. But anyway, that's one of the things we can evaluate job rotation paths. Now this is using an example if we don't rotate and we spend 8 hours a day at 3 stations, and each station has a physical demand here with the fatigue failure theory for the shoulder tool. It calculates shoulder torque and then the number at the moment, and then the number of times you do it, and it calculates the cumulative damage, then a probability of an outcome, which is either, I believe it's an injury and or an office visit, like a visit to the plant nurse or medical report, that kind of thing. So station 1 is have 38.5% chance of an outcome. Station 2, 37.5. Station 3, 13.1 percent chance of an outcome. So station 3 significantly lower risk than the other 2 stations are about the same. But our total probability of an outcome is adding those together, and over the course of a year would be 0.891. So it's approaching 1, the chance that we have either an injury or a medical report, at least one of those over the course of a year. Okay. Now if we do rotation, it's those same demands, but we spend a third of the shift at each station. You can see the cumulative damage, and then it adds up to a total cumulative damage for the shift exposure is 34.3%, and our probability of an outcome would be 3 times that, because we have 3 workers. It would be 1.029. So notice our probability of an injury actually increased with rotation, and it's very common to see that. But it's interesting, 2 of the jobs, station 1 and 2, those employees, their risk actually improved. It went down to 34 instead of around 37, 38. It went down to 34. But the poor old the one that was green, it went from 13% up to 34.3. But one thing these tools allow us to do, rotation a lot of times is a kind of a fact of life in, say, automotive assembly or much of manufacturing. And these new tools enable us to calculate rotation path exposures and also cumulative probabilities, where with single task models it really just wasn't, you could do some weighted average or something, but it really wasn't based on, kind of rhyme or reason, because things didn't really add up. You just statistically were kind of making it work out. But that's the strength of the multitask models. They also have high application utility. And traditionally, the single task, I worked in industry, many, and as a consultant many years, and typically you complete your risk assessments and they're obsolete kind of the day you complete them. Things change, and after a lot of times 2, 3, 4 years, you realize they're obsolete, need to be updated. So they're like snapshots in time, and you're always looking backwards. But one thing we can do with the multitask models is we can actually use them to forecast if we have changes to like operational parameters, things such as cycle time or make model mix. Say next week we anticipate some overtime. We could actually, since these models are continuous in nature, and you don't have a single, like an average or a worst case input, you make a change to one force or you change something such as cycle time, it's easy to calculate what the change is going to be. So here we can see, okay, what's the impact of anticipated overtime? Or maybe we're going to have a make model mix change. I can think of an example. I was working in a company a couple of years ago, and when I first got in there, they had 2 shoulder injuries. Well, they had like 13 or 14 make model mixes that they ran, and there were 2 of them that they rarely ran, but those were really difficult on the left shoulder. And they just happened to have some, the sequencing of their orders or whatever, they ran those for 2 consecutive days, and there's like 2 or 3 shoulder injuries due to that, and there was hardly any way to forecast or predict that. But with these multitask models, particularly if you account for the differences in make models, things like that are easily or much more readily calculated, I should say. And I've heard situations, for example, management want to know, okay, what if we go from an 8-hour shift to a 10-hour shift? What's going to be how's that going to impact our risk of injury? Or those types of change, or changing the cycle time. They're just not, single task models, it's not really easy to go back and update those, but it's much more easier, I found, with multitask models to update them. Now, this is the concept of an ergonomic control panel, to where we can things such as shift duration, cycle time, make model mix, where you can have your evaluation info digitally recorded, a digital version of it, and then you can play around with slider bars or things to see what changing these operational parameters will have on your resultant risk. And this is kind of an example of how you might have a dashboard and you change. And I have working one of these in Excel to show sort of how you can demo. You can change cycle time or make model mix, and you can. It's awesome. You can just see the numbers instantly change as you change those parameters. Okay, and also the concept of an ergonomic control panel. We can have access evaluation data at every level. I think of this as a drill down menu, where you say you be out on the floor with a tablet and you want to see the metrics for this line or this individual. Say we're on line 1, we want to see station 2 or station 1, and then I want to see task 4. So to go from from line to the station to the department, to be able to instantly access the metrics and then have access to something like a control panel and that's kind of my co-author and I have sort of developed innovative concepts for how we can better apply these technologies. What are the things we can do with them? And you have to kind of envision it or imagine it, but before things happen. But some of these things, certainly with multitask models, we have the technology to do things like this. One thing, as far as really on the practical side, and I've had some good luck with the consulting projects with multitask models, is they're really good to help you see what needs to be what do we need to fix. So you typically with a single task model, a job would have like a high, moderate, low rating, but with the multitask, we can see which individual steps. And most things in life tend to follow Pareto or 80-20, and we don't need to fix everything about the job. A lot of times there's a subset of things. Now we can identify, hey, I need to fix these individual steps or these individual subtasks. So you can see the metric, and you can sort of take your metric output and accumulate it by task or step. I've done it by location. Okay, this is where you get it from the cart, the shelf, or the table, and you can see, oh, shelf 1 and shelf 3 are where are the most problematic. Or I've even done it by item weight, and sometimes you see the heavier items. And I remember one job in particular was very complicated. I think there were about 30 different tasks, and these were in locations for a picking job. But then we simplified that, and in the end, it turned out, the problem was the things over shoulder level that were the heavy items. And in hindsight, that was kind of obvious, but not when you're just looking at the raw stuff happening really fast, and people doing the work, and is there performing the work, and you're trying to kind of make mental. There were so many things going on, you couldn't really mentally process it. But you could, using the multitask models, you could evaluate it. And kind of get a command of it, and figure out where the problem was. And it helps us, and that's these models help us better understand where the risk of injury is coming from, what specific things or locations or weights, and then we can really target our solutions. Okay, they allow us to evaluate work better. You can address the true multitask nature of work. We can understand and evaluate job rotation. We can evaluate the impact of incremental changes. So if we make a small improvement to the job, we expect the risk to likewise improve a little, and vice versa. If we make the job, if we have to add something, you would expect the metric to get a little worse. But with single task models, a lot of times what happens is the metric, you make the job a little more difficult, and the metric gets better, it improves, which again is kind of the converse of the example we showed in the presentation. And we can also quantify the effects of proposed changes. So we have solution concepts. You can run a simulate what the benefit is, and see and quantify it. Hey, if we make this change, we're going to improve the metric from this to this. It's much more kind of fluid and dynamic because it's a continuous metric. It allows us to do cool things like this. Okay, well, that's the end of the presentation. There won't be any questions. I get off easy tonight because it's a recording, but I hope you were at the conference, and if any of you have any questions, reach out to feel free to reach out to me or Bob, and we'd be glad to help you answer those questions. Anyway, thank you very much.